Okay, here we are with non-steady state diffusion. Of course, our application was carburization. On this topic, there's 6 shorter videos. Hopefully that makes it easier for you to just take a bite out of this topic a little bit at a time. This first video is just going to be about the application of non-steady state diffusion to carburization. So the first graph here, the first slide, shows a graph. The y-axis over here on the, over here on the left is ultimate tensile strength, and on the right, it's Brinell hardness. And so if I have, here's percent carbon, if I have a 0.2 weight percent carbon, that'd be a 1020 steel, then I could predict its hardness at just under 150 on the Brinell scale, and the strength of just a little over 400 megapascal. This other line here is the impact toughness, and I deleted that y-axis, so just ignore that. So if we were wanting to harden the surface of a steel, not pay for an expensive high carbon steel, but just harden the surface with diffusion of carbon, it's called carburization. And the carbon concentration of a steel is the only thing that determines its maximum hardness, the value of its maximum hardness. Heat treatment, which we'll talk about in a while, heat treatment would determine how close we could get to that maximum, but the maximum itself is predicted by the percent carbon. So here we have in the bottom here, this description of this graph. If I was asked to have a steel with a surface hardness of, say, 250 on the Brinell scale, I could come over here and see that I need to have somewhere about 0.9 weight percent carbon. So, for example, I just step this out here. If I needed a steel that had 200 HB, 200 Brinell hardness, and I needed that to a depth of 2 millimeters, my first step would be to figure out how much carbon that would take. And so I'm reading over here to the Brinell scale from my 200 value. Then I read down, and it says I need to have a steel with 0.55 weight percent carbon in order to be able to achieve that hardness. Now, that's, like I said, the maximum hardness, and reaching the maximum would be also a function of the heat treatment that I use. Here's our equation for steady state. I talked about this a bit already for both classes, but I wanted to get it in the notes. This is this non-steady state equation here. Here are our terms. So on the left side of the equation, I have something like a concentration gradient. C sub 0 is the original carbon concentration of a steel, the base concentration. C sub s is the concentration that I'm exposing the surface to, and C sub x is the concentration I have at depth x. On the right side of the equation, I have that depth. That has to be in meters, because diffusivity is in meters squared per second. So the time is in seconds. This error function is possibly a new function for you. The complete error function goes from -1 to +1, as x goes from -3 to +3. We are only going to use the upper right quadrant for values of error function of x from 0 to 1. Here's the table. You see they use z here, but when z or the function that's being acted on, the value that's being acted on, when that's 0, then the error function of it is 0, and when the value of z approaches 3, the error function approaches 1. Okay, so let's talk a little bit about the limits of the equation. First of all, here's my equation again. I'm going to think only about what happens if I change x. What happens if I change the depth to which I want to get a certain amount of hardness. If I increase x, that just means I want the hardness to be deeper into the steel. So if I increase x, we know that x over 2 square root dt, that would also increase. That's what it says here. And if z increases or x increases, the error function of that value also increases, and it approaches 1. So the right side of the equation, 1 minus the error function of z, would approach 0. And if the right side of the equation is equal to 0, the only way to make that true with the left side is if c sub x is equal to c sub 0. So as the depth gets deeper and deeper, the concentration at that depth will approach the concentration of the steel before you carburize. Okay, what about time? If I think about time increasing or decreasing. So time, lowercase t, is duration of the process. If it's large, that means I'm going to carburize for a longer time. If t increases, then this function here, this amount, x over 2 square root dt, that would be decreasing. And if that's decreasing, if x is decreasing, then error function of x approaches 0. And 1 minus error function of x approaches 1. So for the whole entire right side of the equation to equal 1, the only way for that to be true is if the numerator is equal to the denominator. And if c sub x minus c0 is equal to c sub s minus c0, that just means that c sub x is equal to c sub s. So as time increases, the concentration of carbon at depth x approaches the carbon concentration at the surface, what we're exposing the steel to. Finally, temperature, uppercase T. Now, temperature itself isn't in this equation, but temperature affects diffusivity D. So if I increase the temperature, that also increases D, which would decrease this quantity x over 2 square root dt, which means that the error function of that would approach 0, and the total right side of the equation would approach 1. And then again, that's only possible if the concentration at depth x is equal to the concentration I put at the surface. So if I run this process at a higher temperature, I approach having the concentration at depth x is equal to the surface concentration.